And the acceleration that we're going to use, the number that we're going to use is 9.8 meters per second. And the reason why we use that as for gravity, right? That's the acceleration of gravity. We use 9.8 because we are measuring in meters. What's the other one, by the way? If it's not 9.8, it's the other one. I forgot the other one off the top of my head. No biggie. No biggie. Right? But 9.8 meters per second because we're using meters.
Isn't it pounds?
Huh?
Pounds?
No. It's no.
Anyway.
So if you multiply that, 10 times 9.8, you're going to get 98 kilograms meter per second, right? Which we call Newton, which we call 98 newtons. Right? Came from the father of calculus, one of the fathers of calculus. They actually call him the father of calculus. There's another one too. Newton, okay? That's where it comes from. All right? Makes sense? So that's how you have to find the force before you find the work. Now that you got the force, right? Because why? Again, why do we do this to find force? Because they gave us the mass in kilograms, right? Okay? So you got to find the force by doing mass times acceleration. Then once you get that, the force, now we can do the work formula. Force times distance, okay? So then the work is equal to force, which is 98 newtons, times the distance, which is what? 25 meters. And you multiply that into your calculator, and you're going to get 490 Newton.
No, you get 2,450.
Oh, that's what I meant. 2,004. Really? You get 2,450?
I have it right here.
Dang it, man, this is my own, this is not good. Okay, 2,000? Good, okay, 2,000.
2,450.
450 Newton meters, right? Which is joules. 2,450 joules. So from now on, we'll just start using joules, okay? I mean, it's not a capital J either. When you write it, use a lowercase, all right? I don't know if that matters, but
It does matter.
chemists, you know, they're physicists are particular, they're little units too. Okay? All right? They're hybrid mathematicians slash engineers, okay? They're a different breed. Got it?
Mm-hmm.
Different breed of person. Y'all okay? Sounds like I should check my work. All right, here we go. Third one. All right. A box-shaped tank. I think I'm gonna hire a student worker to come just erase for me.
I'll do it.
You do it?
I'll
Yeah?
do it.
You'll do it? You'll be a student worker? I mean, get hired as a student worker.
Oh, sure.
So you won't do this for free.
Oh, I don't care.
Okay. You sure you want to erase it? I have to erase it?
Yeah.
Okay. Just don't get your hands dirty though.
Oh, boo.
With a marker, I'm just saying. Okay. If I can talk you out of it.
You know what I do for a living?
I think I know what you do for a
You
living.
do know what I do for a living. It's a dirty job.
What is it again?
I'm a chef.
Where at?
Oh, right now I'm at Longhorn.
Oh, okay.
But I
Well,
was
she's
at.
always making
But
me
I was
stuff.
at the. Yeah, I was gonna make some banana bread for Tuesday.
Oh, cool. Okay, here we go. Okay, I'll get back to that. We'll get back to that conversation later. Here we go. A box-shaped tank is 3 feet long, 5 feet wide, and 6 feet tall. Right? So length, width, and what? Height. Okay? That's how you find volume, by the way, of a box. Length times width times height, right? And it says if the tank is filled with water, how much work will it take to lift the tank 8 feet? So you fill up with water, right? And I want to lift that tank 8 feet high, right? How much work will it take? And it says assume the water, watch this, assume the water weighs 62.4 pounds per cubic what? Foot. See that? So it's going to be let me write that out, 62.4 pounds per cubic foot cube. Got it? Okay. Now remember, force is equal to weight. We need to get the weight, okay, of this thing. So the weight of this entire object is going to be the box, right, times how many pounds of water per cubic foot, right? That's how you're going to get the amount of pounds. You understand? Right? So you got to get, so in other words, the force is equal to the weight, and the way you find the weight with this, with box and water, is going to be volume of the box, right, times the weight density, which is the water. Okay? How many pounds per cubic foot, right? Y'all okay? So that's how we're going to get the weight, which is the force, right? So then you're going to multiply the length times width times height. It's going to be 3 feet times 5 feet times 6 feet. And I have to do this because you're doing physics. You got to be real careful with the units, okay? In math, you can get away with it. We don't have to do all this stuff. 62.4 pounds per feet cubed. Okay, the weight density. Now, if you multiply all that out, 3 times 5, well, let me do a better job. 3 times 6 is 3 times 6. 5 times 6 is 30. Times 3, that gives me what, class? 90? 90 feet, what? Cube? All right? Times the what? 62.4 pounds per feet cubed, right? Yes, and see, this feet cube is going to cancel out with this feet cube, and that's why you have to do that, so you can be left with pounds, right? So you got to go volume times water density. And when you multiply that out, this is what I get. I know you're going to check me on this, right? 5,616 pounds. Did you get that?
Yes.
Okay, good. Now we're not done. That's just the force, right? Now that we got the force by multiplying volume times weight density, now we can find the work. So the work is going to be the force times distance, which is going to be 5,616 pounds, okay? Times, we're going to lift it up 8 feet, the distance. When you multiply that together, it's going to be in standard metrics. So it's going to be 44,928 foot-pounds. Okay? So I don't know if you are become an engineer in the oil field or anywhere in the United States of America, okay, that's probably the units they might use. I don't think they'll use joules. I could be wrong. Just depends. Just depends. I think it depends on what the head engineer is.
They have done wind turbines and we use newtons and joules.
See, there you go. Glad you brought that up.
Torque ratios and everything like that.
Which is, you should, because it's standardized around the world, right?
A bunch of the companies that own them are from overseas, so.
Exactly, see? And sometimes you gotta communicate with other people from other countries, and you gotta learn to get those units. You gotta use joules, not foot-pounds. Right? Okay. Here we go, last one, and then we're going to the calculus part of it. See, y'all okay, class? You getting this? Volume times weight density, all right.
Oh, I'm fired.
Number 4. Oh,
I got fired.
you got fired, yeah, you're not fast enough.
Heard. I'll do better.
All right, a box-shaped tank is 2 meters long, 3 meters wide, 4 meters tall. But if the tank is filled with water, how much would it take to lift the tank 5 meters? Assume the water density is 1,000 kilograms per meter cube. Now watch, this is kilograms per meter cube. Remember, kilograms don't have, the last one was pounds, meters cubed, right? Right, y'all see what I'm saying? But this is kilograms, it's just mass per meters cubed. So this is going to be a little different. It's not just like example 3, okay? Because you don't have no force to it. So you're going to have to find force differently, all right? And the way you find force, because remember, it's just mass, it's just matter, kilograms, right? You got to do mass times acceleration again, all right? Excuse you, okay? But here's the thing. To do this, to do mass times acceleration, when you have water density involved, the mass is going to be density, okay, times volume times acceleration. Are y'all with me? So your mass is gonna be density times volume times the acceleration. So density times volume is your mass, okay? All right. Now, in short, the way they call that symbolically, it's gonna be the Greek letters rho, V, A. The rho, that looks like, that's the Greek letter rho for density, okay? They use that in physics. All right, so do this math. We're gonna get the density, they gave that to us, it's 1,000 kilograms per meters cubed, okay? Times the volume, which is gonna be 2 meters, times 3 meters, times 4 meters, times the acceleration, which again is gonna be 9.8 meters per second squared, okay? And we're gonna multiply all that out. And when you multiply all that out, you're gonna get 235,200 joules. Because again, you're gonna get kilograms. Watch this. This right here is gonna give me what? 2 times 3 is 6, 4 times 6 is 24. 24 what? Meters cubed. Watch this, the meters cubed cancels out with this meters cubed. And then you're gonna be left with units of kilograms, meters per second squared, which is joules. Got it? Okay? So it's joules. I mean newtons. Darn it. It's newtons. Son of a gun. Y'all in class? Newtons. Y'all okay? Not joules, newtons. All right? Now we do the work. So now we can find the work. So now the work is equal to force times distance. The force is what we just found. 235,200 newtons. Times.
Not joules.
Not joules. The work is joules,
My bad.
right? No, it was my bad. I messed you up by saying that earlier. Times 5 what? Meters. The distance, that's work. Force times distance. We have to find the work. If they're given the density in kilograms per meter cubed, you have to go density times volume times acceleration to get the force. But once you get the force, which is in newtons, then we multiply it to the distance, which is in meters, and then we'll get Newton meters. So when you multiply all that out, you're gonna get, I got this. I'm not too confident now because I messed up with the last one. Newton meters, which is joules. Okay? Did y'all get that answer? All right. Got it? All right, man, now we're gonna do some calculus. I don't know, I'm running out of time here. We got about 10 minutes. So far, so good? Let's rock and roll. All right, let's do it. So here we go. It's not many examples. I might be able to knock it out. I don't know. I'm not confident. You know, I got a history that I don't knock these things out real quick.
Speed session, go.
See, my
Oh wait,
person's not even
I'm
the
going.
same.
I'm going. I'm going.
Fired. You are fired. You're doing great.
Gotta be like the race car drivers, right? When they change the tires. I love that, man. That's so cool. Watch them do that. Man, I was like, man, they just get after it, man. All right, ready? So here we go. Let's do some calculus. By the way, before I do, well, I won't even have the formula up here. What's up with that, guys? Okay, let me just give it to you because of time. I ain't gonna show no proof, I promise. The work, to find work in calculus is gonna be the integral from A to B of the force times distance. See that? F of x dx. That's it. That's how you find work. Okay? So here we go. Example 1. First thing we gotta do is find the force. So it says a 10-pound object is lifted 40 feet from the ground to the top of a building using a cable that weighs, watch this, that weighs a half a pound per what?
Foot.
Foot. Notice that the cable, right, the weight of the cable okay, is connected to weight here, okay? It's half a pound. The pound, or I'm going to say this, the weight is connected to what per foot? Does that make sense? The poundage is per foot. So it's always going to be a half a pound per foot is the weight of the cable, right? So therefore, the weight of the cable depends on the length of the cable, right? But what's going to be happening is we're going to pull this cable up. Guess what the length's going to be doing? It's going to be shortening, right? So the force of that cable, or the weight of that cable, is going to get smaller and smaller and smaller as we pull that cable. Are y'all with me? Okay. Now, having said that, let's go ahead and find the force. Well, the force, F of x, is the weight, the pounds. We know that the object, let's see here, is a 10-pound object, right? So we know it's going to be 10 pounds plus the weight of the rope, right? But here's the thing, though. Okay? The weight of the rope, well, remember, it's 40 pounds. It's 1/2 pound per what? Foot. We need to see how long is the rope. Well, the rope right now is 40 feet from the ground to the top. So to get the pounds, we got to multiply 40 times what? 1/2, right? 40 times 1/2 to get the pounds of the rope. Because the pounds of the rope corresponds to the length of the rope, right? But here we got to also take into consideration that we're going to be pulling this rope up, right? We're losing distance, which we call distance x. And we know we're going vertically as a y. Distance x. You see the x here? Right? Okay? So therefore, we are losing distance. So as I bring that weight up, that rope, I'm losing x amount of length of rope. You see what I mean? And every foot of rope I'm losing 1/2 pound, right, of the weight. So I got to subtract 1/2 times x from that. Are y'all with me? So far, so good? Questions on that? Any questions on that? Okay. All right. So if I add all this together, that's going to be 10 plus 20 minus 1/2 x, which will give me 30 minus 1/2 x. So there's my f of x. That's all I need. Now I can do the integral. I can find the work. So the work is equal to the integral. And remember, we're going from 0 to 40, right? Ground 0 to 40, right? Because that's how long the rope is, right? So from 0 to 40 of 30 minus 1/2 x dx. And we can do this by hand, okay? So far, so good? All right. So let's take the integral of 30. Integral of 30 is 30x. The integral of 1/2 x is 1/2 x squared divided by 2, which is 1/4 x squared. Now I'm going fast, okay? Let me know if you got any questions, because I got to go fast. Y'all with me? Everyone okay with a 1/4 x squared? Okay. And then we're going to do our thing. We're going to evaluate. So it's going to be 30 times 4 minus 1/4, 4 squared. Minus, and we're going to plug in the 0. Now we don't have to plug in the 0 because we know this whole thing's going to go to 0 when we do that. But just for your note's sake, when you look back to it, you can see what we did, right?
I thought it was from 0 to 40.
That's what I thought. Why is it 4?
Hell if I know. I'm sorry, class. It is 40. Gosh darn it. Because I'm trying to go fast. That's why I don't like teaching fast. I make mistakes. I'm sorry. So I'm sorry, Brooke. Not helping me here, not giving me no peace of mind. Okay.
Yeah, bro.
So 30 times 40 is 1,200. Minus 40 squared is 1,600. Right? And 1,600 times 1/4 is the same thing as 1,600 divided by 4, which is 400. Are y'all with me, class?
Yes.
And of course, this whole thing goes to 0. We don't need that. So therefore, my work, if you will, is 1,200 minus 400, which is 800. Now, if you look at the units, our units are in feet, and we're looking at doing it in pounds, right? So it's foot pounds. Okay? Foot pounds. Got it? So far, so good? All right. so everyone's okay with the -1/2x, you understand why we're doing that, right? Because we're losing the pound, we're losing the force or the weight of the rope as we pull it up. Because the weight of the rope corresponds to the length of the rope. Yes, ma'am, we're good though? Okay, all right. Okay, now the next two slides are, you got this and you got some extra paper, okay? It's because I gave you some more room here. Now we're talking about a bucket full of sand. Has a mass of 30 kilograms. Remember, not 30 kilograms, that's mass, right? That's doesn't have weight to that. The bucket is to be lifted up to the top of the building 10 meters tall. Now, by the way, the mass, that 30 kilograms corresponds to the bucket and the sand together, okay? So it's the mass of the bucket with the sand, plus the mass of the sand, okay? The bucket is to be lifted up to the top of the building 10 meters tall by a rope of negligible weight, which means the weight is so negligible we don't even count it in the calculation like we did in the last one. However, the bucket has a hole in it and it leaks 0.1 kilograms of sand each meter it's lifted. So every time we lift it 1 meter, we're losing 0.1 kilograms of that sand. Find the work done lifting the bucket to the top of the building. Hint, force is equal to mass times acceleration because it's kilograms, right? For this problem, the force will be the product where the acceleration is 9.8 meters per second squared. Okay, so here we go. So to get the force, you're going to get the force in order to get the work, right? So to get the force is equal to mass times acceleration, which in turn, that's going to be f of x equals, so here we go. So let's start, remember the force is going to be the mass of the bucket, right? Okay? So the mass of the bucket is, remember, it's 30 kilograms. But we're losing mass every time we pull the rope, right? Every meter we pull, we're losing what? 0.1. What does it say? 0.1 kilograms. So we just say 0.1x, right? For every meter. X is the meters, right? Got it? Or we use that much weight, 0.1 kilograms per meter, right? Now, that's the mass times the acceleration, which we know to be 9.8. Now we're going to multiply that 9.8 into the parentheses, thus giving us 30 times 9.8 is 294 minus 9.8 times 0.1x is 0.98x. Got it? So therefore now we can get the work, now we got force. See that? All right, because force is mass times acceleration. So the weight is going to equal to, go from what? We're going from ground zero to what? How tall is this thing?
10.
10 meters. So from 0 to 10. See how the x is in meters here? It's the length, right? Okay. Of what? 294 minus 0.98 x dx. And we're ready to rock and roll. You don't have to come and erase this because we'll go to the next board here. Okay? Good job. Good
I'm
job.
doing the do in my brain every single time.
Okay. Right? So here we go. So we got, I want you to write that work again. So it's going to be work is equal to the integral from 0 to 10 of 294 minus 0.98x dx. So we're going to take the integral of that thing. The integral of 294 is 294x minus the integral of 0.98x is 0.98x squared divided by 2. Okay? What am I doing? And we're going to evaluate that from 0 to 10. Well, if you divide 0.98 by 2, that's going to give you 294x minus 0.49x squared. From 0 to 10. That's an x squared, by the way. Okay? And then we plug in our numbers. So it's going to be 294 minus, 294 times 10. 294 times 10 minus 0.49 times 10 minus Right, it's just 0, right? Oh, forgot to square the 10. Got to square the 10. 294 times 0 minus 0.490 squared. Okay?
Bless you.
Bless you. When you do that, 294 times 10 is 2,940. Minus 10 squared is 100. When you multiply 100 times 0.49, it's going to move that decimal over twice, giving you a 49. This whole thing goes to what? 0. Okay? So far, so good? And just subtract them. We got it. 2,891. Right? But it's kilograms, meters per second squared. That's joules, right? All right. It's 11:54. I got two more. Go ahead and read. Go ahead. I got two more examples. Okay. All right. Some of you have to leave. Do you want me to knock it out by video, one at a time?
I prefer to see it, but that's just me.
Prefer to see it?
Yeah.
I can do both. If you got to leave, go ahead. I will do it by video. All right? I will do it. If you can stay, then I'll go ahead and do it right now. But don't feel forced to have to stay because you got some. It's already time. I got to respect your time. Okay? Don't feel like you have to stay. I will do it by video. So no worries. All right. So here we go. Integration application work. So now we got this trough, right? A trough is 4 meters long, 2.5 meters wide, right? 5 meters deep, okay? The vertical cross section of the trough is a triangle, okay? Which the length of it is 5 meters, and the width of it is 2.5 meters. The trough is full of water, and the density of this water is 1,000 kilograms per meters cubed. Find the amount of work in joules required to empty the trough by pumping the water over the top, okay? And we're going to use, for gravity, G, 9.8 meters per second squared, as the acceleration due to gravity, right? So again, in short, the question is, what we're doing is we need to find the work, need to pump the green layer of water, see the green layer of water? Out from the what? The top, okay? Make sense? All right. Now it says, now they did all this right here, but I'm going to show you where they get that at. That's cheating, okay? I'm going to show you where they get that. I'm going to go to the next slide here. But by the way, let me show you what these measurements are doing here. So right now we know that the height of the trough is 5 meters, right? The height of the layer, this green layer of water, right? The green layer, okay? It's green water, okay? This layer of water from the bottom to that green layer is some distance xi. We don't know what that is, okay? And we know, but the rest of the distance from that green layer to the top, right, is the entire distance, 5 meters, minus this distance xi that we don't know. Got it? Okay? And this delta xi here, I'll show you where that comes from here in just a second. That's actually the width. So the width here, this green from, I don't know if I should use green or not, but the width from here to here, that's your delta xi. Got it? Okay, from here to here, that's your delta xi. That's the width, okay, of that green layer. Make sense?
Yes.
Okay. All right. Now it says the volume of this thin layer is length times width times what? Height. The length, again, is 4 times the width, which is 1/2 xi. I'm going to show you that here in the next slide here. Okay? 1/2 xi. I'll show you where that comes from. Okay? Times delta xi, which is the width. So it's the length times the height, 1/2 xi times the width, delta xi. They don't write it in the form, in the order that they have the formula here. So this is length, height, and that's width. Okay? And I'll show you with the 1/2 here in a minute. And then what they do is they're going to find the force by taking the mass times acceleration. But because this is water, we're looking at density. We're looking at density times the volume of the trough times the acceleration. Okay? So the water density is 1,000, right? Kilograms per meter cubed, times the volume, which we get this from. We got this, the 2xi delta xi, from this. Okay? Times 9.8. And that's how you get the force. But I'm going to show you all in detail in the next slide here how to get all that. All right? I'm just going to say that and just go on. All right? I should have just taken that out. Let me show you where they get that 1/2 from. Okay? So they got that 1/2 from by taking the cross section. What's the cross section? That triangle, right? Okay, we'll go to the next slide where I got some room. See the cross section there? So that 1/2 xi, I'm going to show you how they got it. So what they did was they used similar triangles. Okay? All right. And so what they did was they say, okay, that green layer, all right, that cross section of that triangle, that green layer, the width is 1/2. That's just the width. We're just going to call that W for right now, okay? We don't know. I want to show you where the 1/2 xi comes from. We just call that W. And the width of the entire cross section of the trough is 2.5, right? So we write that as a fraction. We're going to go 2.5 over the width of the entire cross section of the trough over the width of the cross section of the trough up to the green layer, right? The small triangle. Make sense? Is equal to this. So when you have similar triangles, you can do it. You can set the proportion. Okay, it's equal to the fraction of the heights. Okay, so the height of the entire trough, right? That triangle is 5. Cross section of the trough is 5, which is the height of the entire trough, over the height of that green layer, which is x. Okay? So far so good? And then we cross multiply. So 5 times w is 5w. X times 2.5 is 2.5x. And what I'm trying to do is I'm trying to find the width of that green layer of that cross section, right? So we divide both sides by what? By 5. Yeah. And 2.5 divided by 5 is 1/2 x. And that's where they get the 1/2 xi there. Okay? So this right here, I'm writing way too big here, is the width of the base of the small triangle. My goodness. Wish I could be perfect in everything I do. Green layer. Let's do a green layer. Okay. Got it? All right. So from there, once I know that, right, now I can find the volume of that thin layer of water, that green layer. Make sense? Okay? How do you do that? Well, it's going to be the delta V, right, is equal to length times width times height, which is going to equal to 4. The width is 1/2 xi, and the height is delta xi. Okay? Right? Right? It's just the x, right? We call it delta xi. Because it's changing, by the way, as it's pumping out. You see what I'm saying? So we just don't call it x, the height, because that height is changing as it's pumping out that green layer of water, right? The height is diminishing. So we call it delta xi. All right? Make sense? So we're pumping out rectangles, or little small rectangle layers of this green surface, right? That's why we call it xi, little square intervals. Okay, we're pumping out interval layers. Make sense? Okay. Now that we got the volume, now we can take this. Go ahead and multiply it out. 4 times 1/2 is 2 x of I delta x of I. And that's where they got the 2 from in that last slide, okay? So I told you I was going to show you where they come from with that. Now, having said that, that's your volume, right? Why do we need that? Because remember, we're trying to find the what? We're trying to find the force, delta force. Okay, the change in force. Well, that's equal to mass times acceleration, but because our mass is, right, is kilograms, right? And we're dealing with water, we got to do it by density times volume times acceleration. Okay? The density, we already found, we know it's going to be 1,000. The volume, that's why we did this. So we can find the force, okay? Because force is going to need volume. That's why we did all this, all right? And our volume is what? 2xi, right? Times what? Delta xi. Okay? Times the acceleration, which is 9.8. Okay? And when we do all that math, it's going to be 1,909, 119, I can't talk. 19,600, right? xi, delta xi. Right? So see, now we got the force. But we have to do all that work to get the width of that green layer so we can find the what? Force, which is mass times acceleration. And because the mass is density times volume times acceleration, we have to find the volume of that green layer by doing all this here. To do this here, to do this work. Make sense? Okay. Now that we got the force, now we can find the work. Okay? We can set up the work. Make sense? Okay. Well, to find work, we need to know the distance. The distance that this layer is moving, remember the layer's right here. The distance that this layer is moving is 5 minus x. Right? But remember, this is shortening, right? So this is by intervals, by the way, okay? Right now. So basically the distance, I'm gonna write this out. Distance, the layer, the green layer, of water is 5 minus x sub I. Okay? So therefore, now we can find the work. The change in work is equal to the force times distance, right? Delta F times delta D. And delta F we found to be not 1,000, yeah, all that stuff, right? 19600 x of I, delta x of I, times 5 minus x of I. Right? So far, so good?
Mm-hmm.
And then we're going to write a Riemann sum. So we're going to say the limit as n goes to infinity. We got infinite many layers we're pumping this thing out of, this green layer, right? Makes sense? We got a lot of green layers we got to pump out, right? It's just not just one. We say one green layer, but you got, as you go down, there's going to be a bunch of them as we go down, right? So the limit as n goes to infinity. The summation of I equals 1 to n, from the first layer to the nth layer of this work here is going to be 19600 x of I, that's the force, right? Times the distance, 5 minus xi. Watch what I do here. That delta xi, I'm going to move it to the end here. See, that delta xi? I put it right here because we know that's going to become our dx when we take the interval. You see where this is going? Right? Oh.
This is awful. I
Right?
agree. I agree.
Now you're not going to have to do all this work like this. I got to teach it like this so you can see where it's coming from. So I'm doing proof at the same time I'm doing the problem. Okay?
It's a lot of birds.
Yeah. It's a lot, isn't it?
It's all right.
So now I can set up my integral. That's why I got you got some blank space. Okay, that's right. So my work is equal to, how far are we going? From 0 to 5, right? From 0 to 5 of 19,600 x times 5 minus x dx. And that's our integral setup, okay? And now I'm gonna work out the sucker. okay?
Right.
So I gotta go to the next slide. The next slide is to working it out. So after that white blank space, you go to the next slide. Good job. You're doing good. You're doing good, Brooke.
Yeah,
Brooke.
Go, Brooke, go.
Brenda. Why do you
It's
keep
okay.
doing that?
You know what? We have this whole like VR in my family. Like my
Yeah.
brother's
Do
Brandon,
you want this
Brooke,
up
Brittany,
here?
Braden, Bryce, and Bradley.
Dude.
And so we get
That's
it all
cool.
the time. I'm totally used to it.
Oh my
And I'm
goodness.
Brian and Brenda. That's my older brother.
That's, oh wow, man. That is so cool.
Do you
No,
want
I
this
like
up
that. Huh? No, you can erase that now, because now I got it written right here. You missed a spot right
Yeah,
there.
You know what? I did, didn't I? It blended in.
So there it is typed out. And so now we're gonna do our thing, right? So we can before we do the integral, we can multiply that 19,600 x into the parentheses, right? And so we're gonna get, well, no, whoa. We're not gonna multiply the entire, yeah, you go, right? You learned well. We're gonna take that constant 19,600 out, but we're gonna just multiply the x in. So it's gonna be 19,600 from 0 to 5, 5x minus x squared. Look how nice that looks.
So much better.
So much better, right?
DX, yeah.
And we're gonna take the integral of that. That's gonna be
5x squared.
5x squared.
divided
minus,
3x.
Do we not
I mean,
divide
x-
that by 2?
X cubed
Yes.
over 3.
5x squared?
yes ma'am, we
Okay.
do. I'm sorry. I scared you there. Minus
See,
x
well-
cubed divided by 3.
You traumatized.
I am traumatized.
I'm so sorry. Oh man, I know, man. It's like, oh my goodness, Mr. Cortez, what are you doing to us? Okay. Now I don't like to write it like this, so really I'm gonna write it as 5 halves x squared,
Yeah.
1/3 x cubed, okay?
Right.
I like when you do that. Makes more sense.
And I'm gonna do it as I plug in the number, so I'm gonna plug in the 5 and the 0 as I rewrite it like that. So it's gonna be now 19,600, bracket, 5 halves of 5 squared, plug it into 5, minus 1/3, 5 cubed, put that all in parentheses, minus, and we plug in the 0. Of course, we don't really have to because we know this whole thing's gonna go to 0, right? So 5 halves, 0 squared, minus 1/3, 0 cubed. Okay? So it's gonna give me 19,600. When I do this math here, 5 squared is 25. 25 times 5 is 125 divided by 2. 5 cubed is 125. 125 times 1 is 125 divided by 3. Just plug that into your calculator. Okay. And you're gonna get 408, 333.3 joules. And there's your answer. And of course, all this stuff went to 0, right? 0, it's gone, right?
That's crazy.
Ready? One more example, and we're done.
Wait, is there? Because I see.
2?
Well, it says. Oh wait, there was another. Hang on, it's fine.
You good? Yeah?
I didn't realize where we were continuing this on year. And
Oh,
so I put it on my
okay.
other page. But we're good. There
yeah.
was an extra space, so
All right,
I'll rewrite it later.
we're almost done. Man, y'all doing good. I owe y'all. I'm gonna owe y'all because y'all stayed in back doing this.
Donuts?
Yeah.
Y'all bring donuts, but I can't eat them. So you gotta make sure you eat those donuts. I can't eat them. I can't eat them. Next seat.
You say that.
I can eat them. Especially the Southern made.
So no
Oh,
pizza
I'm
either?
done.
I wasn't
Huh?
that impressed.
So
You're
no
not that
pizza
impressed with
either?
Southern made?
No, y'all need to go to Amarillo and get cherry donuts. They're bomb.
Cherry donuts.
Wait,
from where?
Sherry?
Cherry.
No, the company.
Is that the company or is that
Oh, no.
the donut?
What's the company name?
I don't know, but it's over by Grand and I-40.
Grant and I-40. Okay, I'll remember that.
It's by my grandmother's house.
I won't.
Watch my
remember.
wife
It's
wake
kinda
up.
in the ghetto, but it's fine.
Watch my wife wake up and she
That's
goes,
how you know what's
"Where's my
good."
husband?"
Yeah.
And she calls me, where you at? I'm heading to Amarillo. What? Why Amarillo? Because they said these cherry donuts are the bomb. and
Listen,
I
I
can't go taste
hate
them.
donuts. and I will not eat them. But well,
Check those.
I did last time because I
Yeah.
felt bad. But yeah, they're great. Those are the only donuts I'll eat. So.
Oh man, y'all ready for this one?
Sure.
Mhm.
Ew.
Okay, here we go. I gotta do some work here.
We need pie.
Gosh. All right, here we go. So we're gonna find the work needed to raise the water in the cone shown below to the top of the what? Straw. So we gotta show how much work it's gonna take to raise that water from the cone, right? Out to the top of the cone, that's at the bottom of the straw, to the top of the straw. Got it? Okay.
Skin is bill.
Interesting.
How the work is going to take to get the water out of the cone into out of the straw, so you can drink the water out of
It's
the.
not that much.
So the
effort,
force
but-
going through the tube of the straw?
Yes, from the cone to the straw, right?
Okay.
Make sense?
Right.
Mhm.
Now but remember we're doing it by slices, so this is see how it's cut as a slice,
Right.
right?
Right.
So
right,
basically
right.
you have a cylinder going on, right? Each slice is a cylinder, so you're pumping out cylinders of water, and they're very thin, okay? All right, but you have to show it thick so you can understand it's a cylinder. Now those are circles, remember? They're uneven, right? Remember that? We talked about that?
Yeah.
Okay, but when I draw it out, I'm gonna draw them uneven for your sake, okay? All right, so let's say those are my cylinders, those circles are uneven, that's okay, right? Every circle got a radius in the cylinder, right? It's a radius, okay? And it got a thickness. Remember the thickness was y? Well, the height is, no, we called it the r of the y. But here, we're gonna call it delta y sub k. You okay with that? So that's the thickness of the cylinder, right? Now remember, how do you find the volume of a cylinder? Well, volume is equal to the area of the base times the what? The height, right? Okay. So
pi r squared times height.
pi r squared times the height, and this height is delta sub y sub k. Got it? Because we're going vertical, the length, the height, right, of each cylinder. Are y'all okay, class? So far, so good? All right. So the volume of each slice is this. Okay? So the volume, let me write it up here. Volume of slice is pi r squared. Okay?
Wait, but I thought that was the r was the. Oh, I see. Never mind. We're good.
I know when I taught it, it was the
Gotcha.
r's, but now it's the height here, okay?
Yeah, I got you.
As far as the picture's concerned, okay? Why did I, that's horrible handwriting. Delta y sub k, all right? That's the volume of each slice, all right? So far, so good? Okay. Okay. Now we gotta get the R. Let me show you how to get the R. Again, it's all about similar triangles, okay? If you cut a cross section of that cone, right, you got a similar triangle going on, okay? So I will draw it out right here. So here's the cross section of that cone, right? From here to here, the height of that big triangle is 6, right? Okay? And the radius, now remember that the radius is half the base of that triangle. That's the radius. Well, it's 2, right? Okay? What are you trying to do, Cortez? I'm trying to find, now watch this. I'm sorry I'm taking your time. This is how long it takes to teach these things, okay? But watch this. When you're doing we're setting up the integral, right? We're only looking at one disk, but that one disk is a representation, an ambassador of all the disk that's being pumped out of the water. But we had to set it up with just one disk, which represents all the disk. You understand what I'm saying? Okay? So therefore, that one disk is somewhere here, right? And it also has a what? A circle, right? Whose radius we don't know. It's R. Who's right here? It's R. Some radius R. We don't know what it is. And it has some distance here, from here to here, right? Which we call Y. We don't know what that distance is. We'll just call it Y. Are y'all with me?
Yes.
right? So the cross section of the big triangle of the cone, the height is 6 and the radius is what, 2, right? Just from the picture. But this disc right here, which represents a water disc, a water cylinder, if you will, has a what? A radius of its own and its own little height of that cylinder, which is called what? Y. Right? It's like a triangle there, right? And now we can set up we can set up a similar triangle here. So we put the height over the height and the radius over the radius, okay? I'm gonna do it over here on the side. So it's gonna be 6, the height of the large triangle, if you will, right? Over the height of the small triangle, right? It's coming from the disk of water, right? Is equal to the radius of the cross section, large triangle, over the cross section of the small triangle, which is R, right? Okay, then we cross multiply. R times 6 is what? 6R. Y times 2 is 2Y. We're trying to solve for R, right? So we can plug it into that, put it in our volume self-slice formula. So we're going to divide by 6,
Aw, man.
divide by 6.
I was listening to you.
So
and I
R is
divided
equal
by
to
2.
1/3 Y, because 2 over 6 reduces to 1/3 Y. See that? So now I can plug that into R because see that why do I have to do that? Because it's in terms of Y. Right? So you got to put our R in terms of Y. That's why we did all this. Got it? Okay? So remember, so look, guess what? Our R's in terms of Y, like I taught you a long time ago. Matt, right? Whatever the test, just go on. Pi, right? 1/3 Y squared, delta Y sub K. And then we square all that out. So it's going to be pi over 9 Y squared delta Y sub K. Got it? Now we got the volume of the form for the volume of each slice of water that's being pumped out of the cone through the straw. Got it? Okay. So then now that we got that, we got the volume, now we can find the force. Because now remember, this is in kilograms, right? The mass, well, I haven't taught you that yet. Hold on, let me tell you something. Let me show you something you didn't know.
Let me show you
The
something.
mass of water in this problem is going to be 1, okay? I don't know, what the heck, I put grams. Okay, it's the same thing. Instead of kilograms, it's grams, okay? 1 gram per what? Centimeters squared. So sometimes the units could be kilograms, sometimes it could be grams. It's the same thing, right? So that's the mass of water. But it's not pounds, it's not weight, right? So therefore, to find the force, what do? We have to use density times volume times acceleration, right? That's why we need this, okay? So to find the force, delta F sub K is equal to mass times acceleration. We're going to use density times volume times acceleration. The density is 1 gram per centimeters squared. The volume is what we just found, pi over 9, y squared, delta y sub k. And then the acceleration, of course, we know to be 9.81. No, because it's kilograms. So we got to change to grams. The way you changed it from kilograms to grams, just move the decimal place over. It's going to be 981 grams per meters second. Centimeters. Some of them. God, that's, come on, man. Make up your mind here. Centimeter squared, right? Got it?
And that's just gravity, right?
Right.
Okay.
So we're used to 9.81 kilograms per meter squared, right? But because it's in grams, or centimeters, right?
Right.
You have to move that decimal place over twice. 1, 2. Right. 1, 2. That's gonna give me 981 grams per centimeters squared. Right? You have to do that.
Right.
Okay?
Right.
Breathe in, breathe out, multiply this all out. You got 981, we're gonna leave it in terms of pi. So it's gonna be 981 divided by 9 times 1, got it? So basically it's 1 times 1/9 times 981, okay? So 1 times 1/9 times 981 That's gonna give me 109 pi. Okay, y, yeah. I forgot my little k here. Y squared, it's y sub k squared, right? Times delta y sub k, right? And it's gonna be in grams.
Would you not multiply that to each variable in the problem?
Say
Or you
again?
just have to do it to the constant?
Just to the constants, yeah. Because it's just variables, right? Grams per centimeter. Grams per centimeter per. Wait a second, class. Hold on. Are y'all, okay. You know this is not centimeters squared, right? This is what, seconds? Right?
Meters per second squared.
Right, meters per second squared, okay? So it's gonna be centimeters. Shoot. I didn't write the units correctly. Whatever, we're just gonna leave, okay. Right?
Centimeter per second squared.
Mm-hmm. Son of a gun. Basically what I have here is, because I didn't do a good job writing this down, it's grams per centimeter per second squared, the units when you multiply that out. I didn't do a good job showing it up here, so I don't remember how I did it up here. We're almost done, hold on. So acceleration is measured in what? Kilograms per second squared, right? Meters per second squared. Son of a gun. Okay, meters per second squared. What am I doing? And so this is going to be what? Centimeters per second squared, right? No, this is grams per centimeters cubed. We're talking about the acceleration because this is going to be centimeters per second squared, right? Right?
I don't know.
Yeah, it is. Because we moved it over from, we went from what? Son of a gun. Right? Second squared, right? We went from kilograms to what? Grams. And we're gonna go from kilograms to grams. You gotta move that decimal place over what?
2.
2 times. That's how you go from kilograms to grams, but it's grams over a second squared. You got it?
Okay.
Okay? When we multiply this out, it's gonna be grams times centimeters over second squared. Got it? Okay? Right? 1 gram, right?
See,
Times
technically
what?
it's centimeter.
Times centimeter, right?
Wait,
Anyway, let's go on. I'm done. Okay, I gotta get y'all out of here. Okay, I'm gonna go back and just look at that again. Delta, so therefore the work, now we can get the work. Okay? So remember the work is what? Change in force times change in what? Distance. All right, so the work we found, it's gonna be all this stuff up here. 109 pi y sub k squared times delta y sub k. Now the distance. The distance, class, remember we're taking out the water out of the cone, right? So the distance is the length of the cone, 10, but minus the what? Whatever that layer was at, right? That layer of water is some distance y above, right? Right?
Right.
Okay? So it's some distance y. So therefore, the distance when it comes to the work is going to be 10 minus what? Y. 10, the entire distance of the cone minus the what? The distance that that layer of water is from the bottom. Does that make sense? So 10 minus y. You okay? Right? So it's going to be 10 minus y. Got it? Y sub k right now. Y sub k.
Would it not be 10 minus y minus y?
No.
Okay.
No, because this right here is counting this y already.
Okay.
Does that make sense? It's
So
horrible the way they
whole
drew
line
it.
should just go all the the way down.
Yes. it's
But I
'cause
got you.
From here to here should be just from here to here's 10.
Yeah.
I don't know why they have it written up there, that's confusing.
Yeah.
Okay? All right, so then now we can get the work. Now watch this. Check this out. The work is going to be from 0 to 6 centimeters. Does that make sense? Okay? From 0 to 6. Okay?
That's
And the reason why it's 10 because it's considering that 4 and the 6 already. That's where this 10's coming from, by the way. It's the 6 centimeters plus the what?
The straw.
For the bottom of the straw to the cone, right? 6 centimeters plus 4 centimeters gives us the 10 here. But that's already taken consideration here. Does that make sense? Right?
Yes.
Right? Okay? So when we do the integral though, you're not going to go from 0 to 10. You're just going to go from the height of the cone. Does that make sense? So it's going to be what the integral from 0 to 6 of 109 pi y squared times 10 minus y times dy. And there's the integral set up. Son of a gun. Right? And now we can do the integral. Okay? And I'm going to knock it out here. It's easy. It's down here. Y'all okay, class?
Yeah.
Okay. All right. You okay? Got it? We're good?
Yeah.
All right, Brenda, I got it.
Thank you.
Wow. Wow. You gotta be strong all the way to the end, Brenda. I know you want to get out of here. I know you're hungry. All right, come on, let's go. Ready? So the work is equal to the integral from 0 to 6 of 109 pi y squared 10 minus y dy. So factor out the constant, right? 109 pi, the integral from 0 to 6 of 10 y squared, because I'm going to multiply the y squared in the parentheses, and I'm going to take out that 109 pi, right? Make sense? So it's going to be minus y to the, what, third power, dy. Okay, now we're going to take the integral of this sucker. So the integral of 10y squared is going to be 109 pi, bracket, 10 y cubed divided by 3. 10 thirds y cubed, right? Minus integral of y cubed is going to be y to the 4 times 1/4, or divided by 4, right? From 0 to 6. Then we plug in our numbers. 109 pi, 10 thirds, 6 cubed minus 1/4, 6 to the 4th power, in parentheses. Okay, just to save y'all some pain. We're going to plug in the 0 to the y. What's going to happen, Wes?
0.
It's going to be one big fat 0, okay? Right? You know that's going to happen, correct?
Yes.
Just save y'all some time here. And then, you're going to get 109 pi. You're not going to like me here.
Man.
Times 700, so 6 cubed times 10 over 3. That's going to give me 720. 6 to the 4th power, some number, times 1/4. So it'll give me 324. Just use your calculator to get that. You ready? Oh, by the way, the pi is still out here, okay? Got that pi there. So, when you subtract this, what do you get when you subtract that?
3.
Say again?
396.
396. Okay. So we're going to take that 396 and multiply it to the 109. And that's going to give me 43,164 pi. You ready? Watch this. Remember it was centimeters, grams, right? Remember that? Per
Right.
second squared, right?
Right.
Well, you know what that's called? ERG in physics. ERG, centimeter gram second. Okay? Which is CSG units. Centimeters, gram second. Now, but they write it as CSG. Okay? C stands for centimeters, S stands for seconds, G stands for grams. It's called erg. Erg, E-R-G, okay? Hala chihuahua. Okay, now watch this. You ready? Now, one erg is work done when a force is one dyne is applied over a distance of 1 centimeter. I'm not going to write that down. I'll give that to y'all. One erg is work done when a force of one dyne, D-Y-E-N-E, is applied over a distance of 1 centimeter. Don't worry about that. Let's just
The
do it,
laugh.
okay? So, but they want this in joules, right? You ain't gonna say erg, right? So you have to convert it to joules. So we know that 1 erg is equal to 10 to the negative 7 joules. So now all I gotta do is multiply that number times 10 to the negative 7, your calculator. Or just move the decimal place over. So, but you gotta get the pi multiplied into it, okay? So by the way, I forgot to write that down. This is approximately 135,604 erg with a pi multiplied to it. Oh yeah, with me, class?
10 to the negative 7 joules.
Times 10 to the negative 7 joules. So now watch this. So I'm gonna go 135.
Oh my gosh.
604, I think I'm gonna count, ask for off for the rest of the day. Times
Same.
10 to the negative 7. What that means is this, class, when you, right, to turn it into joules. What that means is the decimal in a whole number is always right there. Yeah, that means you're gonna move the main decimal 7 places to the left. Can't talk anymore, right? So you're gonna go 1, 2, 3, 4, 5, 6, 7. And that empty little space there, we fill it with a 0. So basically, that's what you do when you multiply it by 10 times to the negative 7. Are y'all with me, class? So that's going to equal to 0.0135604 joules. J for joules.
It's a lot of work for not much work.
Yeah. Man.
I'm just glad I don't gotta watch a video. It's all done.
So